to study the relationship between the variables. So generally coefficient of correlation is a measure of degree of covariances, like between X and Y variables, whereas the aim of regression analysis, I mean correlation analysis is to study the relationship between two variables, right? Uh, so that we may know the value of one variable on the basis of another variable. So generally, if we see the correlation, we have two ends. One is positive and the other one is negative end. And so coming to the correlation, correlation tests, correlation analysis tests the closeness of the variables. And whereas the regression analysis measures the extent of change in dependent variables, like for X, due to the change in independent variable. So the nature and extent of functional relationship of variables in correlations are studied. And coming to relationships, uh, the causal relationship in variables moving in same and opposite direction is studied in correlation. And even the mutual dependency, like correlation studies the mutual dependence of variables. Then the correlation has the chances in spurious relationship between two variables. Like if we want to study the relationship between two variables, like X and Y, we need to do the correlation. Why to do the correlation means correlation is connecting the relationship between two variables. Then correlation have no scope of I mean, for further mathematical treatment, because that's the end. After finding out the what is correlation between two variables, then there is no further mathematical test to be conducted and carried forward. And correlation is both like independent of change in both origin as well as the scale. And even correlation is a relative measure of linear relationship between X and Y, which is independent of measurement. Like it maybe lies in between positive one. Correlation has very limited scope of application. It is delimited to the linear relationship between two variables. But coming to the differentiation in variables, correlation has both variables are considered at par for study purpose. Then coming to correlation is a symmetric information, that is R of xy, which is equals to ry. Uh, then we have the measurement of covariability of two variables in symmetric information. It means R is both way relationship of x on y and y on x. So it is a statistical test to conduct the correlation, and it's important also. So a correlation coefficient is a statistical measure that indicates the strength and direction of linear relationship between two variables. I have said you already, it's ranging from -1 to +1, positive and as well as negative correlation. If it is indicating with zero, then we can consider it has no relationship. And coming to the strengthening of relationship, the absolute value of correlation coefficient indicates how strong the relationship is. Like value closer to one, it may be either positive or negative. That suggests a stronger relationship, while uh, a value closer to zero, which suggests a negative relation, I mean, weaker relationship. And coming to direction of relationship, a positive correlation coefficient that is between 0 and 1 means that has one variable increases, the other tends to increase as well. A negative correlation coefficient, it ranges from -1 and 0, which means that as one variable increases, the other tends to decreases and vice versa. So the types of correlation we have Carl Pearson's correlation coefficient, which indicates small r. It is the most common type used for linear relationships between two continuous variables. And coming to next one, that is Pearsman rank correlation, which is represented as RHO. So, which measures the monotonic relationship, whether the relationship is increasing or decreasing between two variables, even if it is not strictly a linear relationship. And coming to correlation versus causation, it is important to remember that correlation does not imply causation. Even if two variables are strongly correlated, it does not increasingly necessarily mean that one caused the other. So, I mean, if there are some assumptions of Carl Pearson correlation coefficient, the assumptions are and requirements for calculating Pearson coefficient correlation coefficients are as follows. The data set which is to be correlated should approximate the normal distribution. If the data is normally distributed, then the data points tend to lie closer to the mean. And coming to next one, for all the values of independent variables, the error term is the same. Suppose the error term is smaller for a certain set of values of independent variable and large for another set of values. Then the homogeneity is violated and it can be checked visually through a scatter plot. So scatter plot is nothing but the points are here and there in a graph, and we join these points and we call it as scatter point. So data is said to be an homogenetic if the points lie equally on both the sides of the line for the best fit. So even when the data follows a linear relationship, it is said to be linear. Uh, if the data points are in the form of straight line on a scattered plot, I have said you, then the data satisfies the condition of linearity. And coming to next one, the variables which can take place or the variables which can take any value in an interval are continuous variables. So the data set must contain these continuous variables to compute the Pearson correlation coefficient. So if one data set is ordinal, then Spearman rank correlation is an appropriate measure to conduct. And coming to next one, the data points must be in a pair, which are termed paired observations. So they exist a dependent variable for every observation of independent variable. So there must be no outliers in the data. If the outliers are present, then they can skew the correlation coefficient and make it inappropriate. A point is considered to be an outer if it is beyond plus 3.29 or minus 3.29. It is a standard deviation away. So they can be easily determined visually from a scatter point. So for understanding the Pearson correlation coefficient, I share the formula so that you will understand. And second, I'll share the formula. Yeah. So if you see the formula, we have R equals to N into sigma xy minus sigma x into sigma y by N of sigma x square minus sigma x to the power of x square and into sigma y square minus sigma y whole square. So if you see the abbreviations, yeah. So if you see the abbreviation of the formulas, N is number of values or elements. You just, yeah, number of values or elements, and the sigma x is number of first value list, and sigma y is second value list, and we have sigma xy, that is sum of the products of first and second values. And coming to sigma x square is sum of squares of first values, and sigma y is sum of squares of second values. So this is the way how we need to calculate the correlations. And for finding the correlation is used. So correlation is used almost everywhere in statistics. And correlation illustrates the relationship between two or more variables, as we discussed. It is expressed in the form of number that is known as correlation coefficient. So I've already discussed that correlation coefficient are of two types, positive correlation and the negative correlation. And we have zero correlation, or zero correlation is also known as no correlation. And coming to correlation coefficient properties. So correlation coefficient is all about establishing relationship between two variables. Some properties of the correlation coefficient are like, first one, correlation coefficient remains in the same measurement as in which the two variables are. And the signs, second one, the signs that correlation of coefficient have will always be same as the variances. Then numerical numerical value of the correlation of coefficient will be between -1 to +1. It is known as a real number value. Then negative value of coefficient suggests that the correlation is strong and negative, and if R goes on approaching -1, then it means that the relationship is going towards the negative side. When R approaches the side of +1, then it means the relationship is strong and positive. By this, we can say that if +1 is the result of correlation, then the relationship is in a positive state. So, the weak correlation is signaled when the coefficient of correlation approaches 0. When R is near to 0, then we can deduct that the relationship is weak. Next comes correlation coefficient can be very dicey because we cannot say that whether the participants are truthful or not. The coefficient of correlation is not affected when we interchange two variables. We can put forward or backward and we can test the correlation of coefficient. The coefficient of correlation is a pure number without the effect of any units on it. It also does not get affected when we add the same number to all the values of one variable. We can multiply all the variables by same positive number. It does not affect the correlation coefficient. So correlation coefficient is a pure number without the effect of any units on it. It does not get affected when we add the same number to all the values of one variable. We can even multiply all these variables by same positive number. It does not affect the correlation coefficient. As we discussed, R is not affected by any unit because R is a scale intervariant, we call it. So when we use correlation for measuring the association, but that does not mean that we are taking about causation. By this, we simply mean that what we are correlating the two variables, then it might be the possibility that the third variable may be influencing them. I'll share a screen so that you can understand. Yeah. So if you see this, the problem given to you, X and Y, 50, 51, 52, 53, 54 are the X variables. And Y variables 3.1, 3.2, 3.3, 3.4, and 3.5. So what is N here? N is 5 because there are number of variables N. If you count 1, 2, 3, 4, 5. So N is 5. Number of variables are 5. And what is Y? Y they have already given me. So what you need to do? You need to multiply X into Y. So you get all these values, 155, 163, 171, 180, and 189. How you get 50 into 3.1? You get 155. 50 into 3.2. You get 163.2. So similar to 52 into 3.3, you get 171.6. Then multiply 53 into 3.4, you get 180.2. And 54 into 3.5, you get 189. So then you need to square the x values. 50 squaring of 50. You get 2551 square, 2601, 52 square, 2704, 53 square, 2809, 54 square, 2916. And what is x square? 3.1 square. Then y 3.2 square, 10.24. Then 3.3 square, 10.89. Then 3.4 square, 11.56. Then 3.5 square, 12.25. So like this, we see the table, how to calculate. Then what will be the next procedure? You need to what make the totals, and we call it as summation. Summation of x, add all the x values, 50 plus 51 plus 52 plus 53 plus 50. So you get 260 as a total. So we call it as summation x. And similar to summation y, make the total of all the y values, that is 3.1 plus 3.2 plus 3.3 plus 3.4 plus 3.5. You get 16.5 as the total of y. And now make the total of sigma xy. Whatever we make the totals, we call it as summation or sigma. So sigma xy total means 155 plus 163.2 plus 171.6 plus 180.2 plus 189. What is the total you get? You get 859. Similarly, you need to total it of x square. What is x square? Summation 2500 plus 2601, then 2704 plus 2809 plus 2916. You get the total as 13530. Then you get y square total 9.61 plus 10.24 plus 10.89 plus 11.56 plus 12.25. You get around 54.55. So these are the totals of all the tables. Then we need to substitute in the formula what I have discussed previously. I have shared the formula with you. Yeah. So this is the formula we need to use for correlation coefficient. And whatever the values we got in the table, totals, we need to substitute in the formula. So by substituting all the values in the formula, we get R equals to 1, which shows a positive correlation. So similar to the previous problem, we see the second problem also. I'm sharing the second problem also. Yeah, this is another problem. It is also same to the previous problem. We have given x values and y values, and n is 5. 1, 2, 3, 4, 5. 5 columns. If you see, you get the number of variables, that is n. So x and y values are given. You need to take what is xy. Xy is nothing but multiplying x into y. You get xy values. That is 12 into 2, 24, 15 into 4, 60, 18 into 6, 94, 21 into 8, 168, 27 into 12, 324. So you need to do x square, squaring 12. you get 144. Squaring of 15, 225. Squaring of 18, 324. Squaring of 21, 441. Squaring of 27, 729. Then similarly, y square, 2 square 4, 4 square 16, 6 square 36, 8 square 64, 12 square 144. So after doing this table, make the totals of x, make the total of y, make the total of xy, make the total of x square, make the total of y square. So after making the totals, now we need to substitute in the formula. So after substituting of the formula, what we get the answer is called R. So in this problem, R is 0.84. So these are some of the problems. Uh, it is generally reflected. So if we see the correlation coefficient, it was developed by Carl Pearson from a related idea introduced by Francis Galton in 80s in 1880s, and for which mathematical formula was derived and published by Auguste Barvis in 1844. And naming the coefficient is their motto. And coefficient correlation can be derived by considering the cosine of angles between 2 points representing two sets of x and y coordinate data. The expression is therefore a number between -1 and 1 and equal to unity when all points lie on a straight line. And coming to definition, Carl Pearson coefficient is the covariance of two variables divided by a product of their standard deviations. The form of definition involves a product moment that is the first movement about the origin. We call it as mean of the product, and product of mean adjusted random variables. Hence the modifier product movement in the name. And coming to Pearson coefficient, correlation coefficient, when applied to a population, is commonly represented by a Greek letter RHO and may be referred to as the population correlation coefficient or the population Pearson correlation coefficient. Uh, it is given a random variables like x, y. For example, height and weight. So if we see the mathematical properties, the values of both the sample and the population, Pearson correlation coefficients are on or between -1 and 1. It's a common thumb rule. Correlation equals to 1 or -1, which responds to data points lying exactly on a line or to a bivariate distribution entirely supported on a line. So the Pearson correlation coefficient is a systematic correlation that is xy equals to yx. So a key mathematical property of Pearson correlation coefficient is that it is invariant under separate changes in location and scale in the two variables. That is, we may transform x to a plus bx and transform y to c plus dy. So whereas a, b, c and d are constant with bd which is less than 0 without changing the correlation coefficient. So more, so this holds for the both the population as well as the sample Pearson correlation coefficients. So more general linear transformation do change the correlations. So how we interpret this correlation means the correlation coefficient ranges from -1 to 1. So an absolute change of exactly 1 implies that a linear equation describes the relationship between x and y are perfectly with all data points lying on a line. So the correlation sign is determined by the regression slope, a value of +1, which implies that all the data points lies on a line for which y increases as x increases. Whereas a value of y implies a line where y increases but x decreases. So a value of 0 implies that there is no linear dependencies between the variables or variances. So mostly generally, more generally, um, x xi minus x bar into yi minus y bar is a positive if and only if xi and yi lie on the same side of their respective means. The correlation coefficient is positive if xi and yi tend to be simultaneously greater than or simultaneously less than their respective means. So the correlation coefficient is negative, or we call it as anti-correlation, if xi and yi tend to lie on opposite sides of their respective means. For example, if xi is greater than and yi is also greater than, then it is an anti-correlation, we say it. Moreover, the stronger either tendency is and the larger is the absolute value of correlation coefficient. Coming to Rogers and Niswander, catalyzed 13 ways of interpreting correlation or simple functions of it. So we have first one, functions of raw scores and means. Next one, standardizing covariances. Next we have standardized slope of regression line. Then we have geometric mean of two regression slopes. Then we have square root of ratios of two variances. Then we have mean square cross product of standardized variables. Then functions of the angle between two standardized regression lines. Then functions of angle between two variable vectors. Then we have rescaled variances of the difference between standardized scores. Then we have estimated from the balloon rule, then related to bivariate eclipse of isoconcentrations, then function of test statistics from designed experiments. Then we have ratios of two means. Then we have geometric expressions. I'll just share with you. Yeah, if you see the geometric expression, we have x-axis and y-axis. Uh, and we have this what graph where we see uncentered data with there is a relationship between the correlation variant coefficient and angle between two regression lines, that is y and x, which is obtained by regression y on x and x on y respectively. Um, then for a centered data, the correlation coefficient can also be viewed as the cosine. of the angle theta between two observed vectors in n-dimensional space. And both the uncentered and centered correlation coefficients can be determined for a data set. As an example, suppose five countries are found to have gross national products of 1, 2, 3, 5, and $8 billion respectively. Suppose these five countries in the same order are found to have 11%, 12%, 13%, 15%, and 18% poverty, then let X and Y be ordered five element vectors containing the above data, like X equals to 1, 2, 3, 5, and 8. Y equals to 0.11, 0.12 because calculating the percentages 0.13, 0.15, and 0.18. By using the procedure for finding the angle theta between two vectors, we have a formula. So statistical inferences on based on Pearson's correlation coefficient often focuses on one of the following aims. We have two aims. The first one is uh, aim to test the null hypothesis that the true correlation coefficient is equal to zero based on the value of sample correlation coefficient, that is R. The other aim is to derive a confidence level, that is repeated sampling has a given probability of containing P. So generally, correlation coefficient reflects how similar the measurements of two or more variables are across a data set. So I share what the table, how the positive correlation, how the negative correlation, or else there is no correlation graph will. So if you see, this is the, yeah. So if you see here, we have perfect correlation, perfect positive correlation, zero correlation, perfect negative correlation. If you see the table, I mean graph, how the positive correlation implies. So in positive correlation, when one variable changes, the other variable changes in the same direction. And coming to see the zero correlation, there is no relationship between the variables. It's all in different places. One is here, there. This is called zero correlation. And when one variable changes, the other variable changes in a opposite direction. That is called perfectly negative correlation. So generally, a correlation coefficient is a descriptive statistics. That means it summarizes sample data without letting you infer anything about the population. A correlation coefficient is a bivariate statistic which summarizes the relationship between two variables. So it is a multivariate statistic when you have more than two variables. If your correlation coefficient is based on sample data, you will need an inferential statistics. If you want to generalize your results to a population, you can use an F test or T test to calculate test statistics that tells you the statistical significance of your findings or your answer. And a correlation coefficient is also an effective size measure which tells you the practical significance of your result. And correlation coefficient are unit free, which makes it possible to directly compare coefficient between the studies. In correlation research, you investigate whether changes in one variable are associated with changes in another variables. So after data collection, you can visualize your data in a scatter plot by plotting one variable on the x-axis and the other on the y-axis. It does not matter which variable are placed either on axis. So visually inspect your plot for a pattern and decide there is a linear relationship or non-linear relationship between variables. A linear pattern means you can fit a straight line of the best fit between the data points, while a non-linear or curvilinear pattern can take all the sorts of different shapes such as a U shape or a line with a curve. So how you interpret a correlation coefficient? So the value of correlation coefficient always ranges, I have said you, positive 1 and minus 1. And you treat it as a general indicator of the strength of the relationship between variables. So the sign of the coefficient reflects whether the variable changes in same direction or opposite direction. A positive value means the variable change together in the same direction, while a negative value means they change together in a opposite direction. Absolute value of a number is equal to the number without its signs. The absolute value of a correlation coefficient tells you the magnitude of the correlation. The greater the absolute value, the stronger the correlation. So there are many different guidelines for interpreting the correlation coefficient because findings can vary a lot between study fields. You can use Likert scale for conducting and interpreting. While these guidelines is helpful in a pinch, it's much more important to take a research context and purpose into an account when forming conclusions. So correlation coefficient tells you how closely your data fits on a line. If you have a linear relationship, you will draw a straight line and straight line of a best fit that takes all of your data points into account on a scatter plot. The closer your points are to this line, the higher the absolute value of the correlation coefficient and the stronger your linear correlation. If all points are perfectly on this line, you have a perfect correlation. If all points, if all points are closely your points are, the closer your points are to this line, the higher the value of the correlation coefficient and the stronger your linear correlation. If all points are perfectly on this line, you have a perfect correlation. If all points are closely to this line, the absolute value of your correlation coefficient is high. If these points are spread far from your line and the absolute value of your correlation is low. Note that the steepness or slope of the line is not related to correlation coefficient value. The correlation coefficient does not help you to predict how much one variable will change based on the given change in the other. Because two data sets with the same correlation coefficient value can have lines with every different slopes. Uh, we have types. You can choose from many different correlation coefficient based on linearity of the relationship, the level of measurements of your variables, and the distribution of your data. For high statistical power and accuracy, it's best to use the correlation coefficient that's most appropriate for your data. The most commonly used correlation coefficient is Pearson R because it allows for a strong inferences. It's a parametric and measures linear relationships. But if your data does not meet all the assumptions for this test, you will need to use non-parametric test instead of parametric test. Non-parametric test of rank correlation coefficient summarizes non-linear relationship between variables. If we have good relationships, then we consider parametric test correlation coefficient. Um, the Pearman's RHO and Kendall Store have the same conditions for use, but Kendall Store is generally preferred for smaller samples, whereas Spearman RHO is widely used. The table below, I'll just share the table with you. So I'll share the table. Yeah. If you see these are the types. If you want to note, you can note. Then you have one more thing. Yeah, this is another types. So these are the types of correlation. Then, if you see, if you think correlation, it is nothing but it is made by clubbing the words co and relation. The word co means together. Thus, correlation means the relationship between any set of data with when considered together. So, in statistics, the correlation coefficient is a measure defined between the numbers -1 and +1. So, uh, so this represents the linear interdependency of the set of data. And why we need to study this correlation coefficient means the correlation coefficient is used to measure the strength of the relationship between two variables. As as the class started, I have been telling you it is to know the uh, strength between the variables, two variables or more variables. So generally, the value of correlation should ranges from -1 to +1 only. We have already discussed. So this means that any value beyond this range will be result an error in correlation measurement. So whenever we do these kind of a problems, the correlation coefficient should range from -1 to 1 only. In between these numbers only your correlation measurement should be there. Otherwise, there will be an error in your calculation. So a correlation of value that is -1 means a perfect negative correlation, while a correlation of +1 means a perfect positive correlation. A correlation of 0 means there is no relationship between the variables. So I'll just share the screen with you. Yeah. So we have these many types of correlation. We have perfect positive correlation. We have strong positive correlation. Then weak positive correlation. See the graphs, how it represents the variables on the graph. And we have no correlation. Then we have weak negative correlation, strong negative correlation, perfect negative correlation. So these graphs are important to understand how the variables are placed on the graph and how we relates correlation coefficient, right? So coming to, there are several types of correlation coefficient as we discussed. So Pearson coefficient R being the most common among all, I have already discussed. So it measures the strength and direction of the linear relationship between the two variables and cannot capture non-linear relationship between two variables. So it cannot differentiate between dependent and independent variables. So finally, I just want to tell you we have a difference between regression as well as correlation. Generally, what is regression? You know what is correlation now. So, correlation indicates the nature and relationship between linear variables. And what regression tells you? Regression tells you the impact of independent variables on the dependent variables. So here variables have positive, negative correlation, but in regression, uh, for every unit increase in x, there is an corresponding average increase in y. That is bxy we call it as, or byx. Uh, for a negative regression coefficient, for every unit increase in x, there is corresponding average decrease in y. We call it as byx. So it is a symmetric for both, we say x and y in correlation, and it is non-symmetric for both, say for variables x and y, that is bxy and byx have different interpretations and meanings as well. uh, for example, I share the differences between correlation and regression. See the table. This is differences between correlation and regression. It is a basic difference. You should know what is correlation means and what is regression means. So next we have the difference between covariance and correlations. We'll see that one also. Yeah, here we have the correlation differences and covariances. So to understand correlation, you know what is covariance. Covariance is the measure to indicate the extent up to which two variables can change. So it is one of the measure of correlation only. So same it lies from minus sigma to plus sigma. It even changes in scale that affects the value of covariances. So with this, I want to conclude my class for today. Thank you, everyone. Thank you.